Okay, so here we go with section 3.6, derivatives of inverse functions. So again, in the first part of chapter 3, we learned all our rules for taking derivatives. And in the second part of chapter 3, what we're looking at here is we're looking at applications of those techniques, ways to use those techniques we learned earlier to take derivatives of more complicated situations. So we did implicit differentiation, then we did logarithmic differentiation, and now we're going to take a look at taking derivatives of inverse functions. Right? So we have two objectives, that is to find the derivative of an inverse function and to differentiate an inverse trigonometric function. Those are our two objectives. First off, we're going to take a look at the definition of an inverse function, just in case you may have forgotten it since you first saw it way back in probably college algebra, or maybe if you took pre-calc. All right, so we're going to start by saying there is a function f whose domain is an interval I. Could be the entire real numbers, could be a small piece of it. If that function f has an inverse function, I want to stop right there because there's a giant word that only takes up two letters. If. Every function does not have an inverse. But if you have a function that does have an inverse, then the following statements are true. First one is, if f is continuous on its domain, then the inverse is also continuous. So a continuous function, if it has an inverse, its inverse will also be a continuous function. And if the function is differentiable on some interval and the derivative is not equal to 0, then the inverse will also have a derivative at those values c. So if you have a function is differentiable on an interval containing a number c, pick that to be any number you want, and the derivative is there is not equal to 0, then the inverse will also be differentiable at that same value. Okay? All right, so here's theorem 3.71. This is the derivative of an inverse function, and it reads, let f be a function that is differentiable on an interval I. If f has an inverse, and we'll call that inverse function's name g, then g is differentiable for any x for which that 0 we talked about earlier doesn't exist. That is, for which the inverse of g of x is not equal to 0. And moreover, the derivative of g can be found by taking 1 divided by the inverse of f, of the derivative of f of g of x. Right? Provided that that chunk downstairs is not equal to 0, because you can never divide by 0. All right, and so basically what this represents is the theory behind derivatives of inverse functions. It does suppose, though, that a lot of items are known or are readily available that you might not have access to. For example, it makes the assumption that you know f, you know g, and you can easily take the derivative of f, right? Which isn't always the case. Okay? And so usually when it comes to taking derivatives of inverse functions, we don't rely on this theorem here. What we usually rely on is implicit differentiation and rewriting a function as not an inverse, but as the original function f. And let me show you what I mean by that. Okay? So here I have an inverse function, y equals the sine of x. So in that definition above, this would be the function g of x. G of x would be the inverse function, and f of x would be the plain old function. And if our job is to find the derivative, that is to find g prime of x, according to that theorem, according to that formula up there, g prime of x would be equal to 1 over f prime of g of x. Right? And I know since I have f here that I can easily find f prime of x. F prime of x would be the cosine of x. So then our derivative down here, g prime of x, could be written as 1 over f prime cosine of g of x. G of x is arcsine of x. And there's my derivative. But I don't like that. And here's why I don't like that, or here's why this would be complicated. It assumes that everyone can look at this, recognize it as being the g, and be able to easily find the original function f. And that always isn't the case. So while this isn't incorrect, more commonly, to find this derivative, we would do something like this. All right, my job is to take the derivative with respect to x of the equation y equals the arcsine of x. I can't do that because I don't have a rule for arcsine. So what I'm going to do is I'm going to rewrite what's inside those parentheses in this way. If y is equal to the arcsine of x, then the sine of y should be equal to x. Right? Because remember how inverse functions work, right? If a function goes from here to there, the inverse comes back. Right? So if this is x and this is y, and we are taking a ride on the arcsine function, what would take me back? Well, the sine function, but the sine function is then saying that the sine of y, which is where we're starting, will end up over there at x, because that's how inverse functions work. Right? If a function takes you from y to x, then its inverse takes you back from x to y. Now I can use the techniques that I learned last section, because this is now an implicit function, but I know how to take the derivative of sine, and I can say then that the cosine of y times my dy dx is equal to 1, and then I can go a step further and say then that dy dx is equal to 1 over the cosine of y. And now I know what you're saying. You're saying, hey, wait a second, that isn't what you had written there a moment ago. A moment ago you had this. You had that g prime of x, which would be the y prime here, was 1 over the cosine of the sine of x? Arcsine of x, right? That. And how are these things the same? Well, if we go back to the original statement, what's arcsine of x equal to? And so I could rewrite this as 1 over the cosine of y. Oh, but wait. It's more complicated than that even. Right? Since the original function was handed to me explicitly, then the derivative that I end up with in the end must also be explicit, and this is implicit. So now I've got to do another thing. Okay, you ready for this other thing? I'm going to go back to trigonometry, and I am going to draw the triangle that represents that scenario right there. The triangle that is represented by that says that the arcsine of a number is equal to an angle y. Okay? So if I make this be my angle y, then the sine of that angle y is equal to x. So I'll put an x there, a 1 there, and a square root of 1 minus x squared here. Okay? Now, I know that some people are probably going to be struggling with that, not liking that. So just as a reminder over here on the side, okay? Trig of angle equals number, or arc trig of number equals angle. And don't forget this. So katoa, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So depending on which one of these you want to look at, if we look at the top one, that says the arcsine of a number is equal to y. So x is the number, y is the angle. And to make the number fit my triangle, I have to make sure that the opposite over the hypotenuse ratio works out to be x. So I chose the opposite side to be x and the hypotenuse to be 1. Okay? If you don't like that, then look at the light blue. The light blue says the sine of y is equal to x. So y is the angle, and x is opposite over hypotenuse. So I put the y as the angle, and then I made x and 1. Now where did this side come from? Well, we have Pythagoras to thank for that, because that is from the Pythagorean theorem. The sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. Okay, so that's where that came from. And now I'm going to use that triangle to simplify cosine of y. Because according to that triangle, what would the cosine of y be? Well, there's y. It's an angle. The cosine is the adjacent over the hypotenuse. So it would be the square root of 1 minus x squared divided by 1, but who does that? It's just 1 minus x squared. And so then finally, that means that I can take that derivative and rewrite it as dy dx is equal to 1 divided by the square root of 1 minus x squared. Okay? So for the arcsine function, the derivative of the arcsine of x is equal to the square 1 divided by the square root of 1 minus x squared. Now this is only true provided that that denominator there is not equal to 0. Remember, you can't have it be equal to 0. Okay? All right. And that same logic can be applied to every trigonometric function out there. So here are the derivatives for the arcsine, the arccosine, the arctangent, the arccotangent, the arcsecant, and the arccosecant. Right? Now, these are the chain rule variants. You'll see that they are not taking the arcsine of x and the arccosine of x. It's the arcsine of a function u. Right? And this looks like it's a lot, but if you look at it for a moment, what you'll notice is that these two are pretty much the same, aren't they? What's the only difference between the derivative of the arcsine and derivative of the arccosine? A negative in the numerator? What about arctangent and arccotangent? Same. Negative in the numerator? What about arcsecant and arccosecant? Same. The only difference is negative in a numerator. And what you'll notice is these are all the C trig functions. Cosine, arccosine, cotangent, arccotangent, cosecant, arccosecant. All the C's have negatives in their numerators. All the plain old trig, no negatives. Right? So what does this look like in application? Well, suppose that someone handed you this and said, what is the derivative with respect to x of the arcsine of x squared plus 5x? Right? Well, you would look at that and say, well, here's my formula. This whole mess right here is u. That means that u prime is 2x plus 5. So then the derivative of this is going to be 2x plus 5 divided by the square root of 1 minus x squared plus 5x squared. And then I'm done. There's my derivative. Okay? What if someone decided to be mean to you and mix things up and asked you to take the derivative with respect to x of the arccosine of xy? Right? Now I've got two problems. I've got a product rule hiding in here, and I've also got implicit differentiation hiding in there, but I can do that. All I'm going to do is say that u is x times y, so then u prime is going to be 1 times y plus x times the derivative of y, y prime, or if you wanted to clean that up a little bit, that's y plus x y prime, and then according to the arccosine rule, It's going to be the negative of u prime divided by the square root of 1 minus u squared. And there's my derivative. Okay. Now, one thing that you will notice about arc trig, what do you think the chances are that for any of these problems, that any of these fractions are going to simplify? Do you think that when you do this, that this is magically going to turn into something that's going to nicely simplify? Or should you expect your final answers to stay pretty ugly? Nasty fractions with these horrible denominators. Right? That is the expectation that you should have when it comes to arc trig. Is that your answer, much like the stuff that we did with implicit differentiation, if I did an arc trig function, if I took the derivative of an arc trig function, and the derivative just kind of fell apart and was no longer a fraction, the first thing that I would say to myself is, how did I screw this up? Because these are not, in general, most of the time, okay, not things that are going to simplify nicely. They are most likely going to stay ugly. You will occasionally have something under the root, like in this one right here, that you could take another step and turn that into negative quantity y plus x y prime over the square root of 1 minus x squared y squared, and maybe do something like that. But there's traditionally not a lot of simplification that's going to happen in these. It just isn't something that occurs. So keep that in mind when you're taking derivatives. This brings us to the end of section 3.6. What are we looking at here for this unit? We have 3, 5, 3, 6, 3, 7, 3, 8. So this will be week 1. Next week we'll do 3, 7, and 3, 8. Actually, I'll try to get those videos up at the end of this week so you can work ahead a little bit. And then we have an exam over 3, 5 through 3, 8. So this is half of the first exam. All right. Have a great day.